want to do the project? Do you want to do Tuesday?
Thursday, I won't be able to work on it all break.
Yeah.
I'm gonna be gone on vacation.
Like I could do some bit of a break. I'm just heading home for a few days.
Yeah, I mean, if you get the models and stuff made up, I can write the report.
Al texted me so many times when I hurt myself.
Okay. If you are ready, we can come back. What's that? Okay, I'm ready. let's come back. Okay. So we talk about why running up. Sometimes it's maybe just not feasible. Okay, like in this case, that's for this oh, sorry. So when we solve it, okay. First, what's a relax? What's LP relax? ILP relax.
They don't have any integers.
No integer constraint. Okay, good job. So you guys are ready. So in the ILP relaxation, this is suppose this is the solution to the ILP relaxation, meaning you remove that integer constraint. You got it here. So you can see that. So the value is like 1 point something, and the 1 point something here. Okay. You think okay. In the previous example, question?
Yeah, can you explain how a relaxed ILP is different than an LP?
ILP relax is you remove the integer constraint from ILP. Okay,
Yes.
here.
But is that just an LP then?
Yeah, it's just
It is?
LP.
Okay.
Here, it's the LP relaxation of the ILP model. So if you just cross this constraint, it becomes the LP relaxation. Okay. Yeah, relax the integer constraints. Okay. Becomes ILP relaxation. So okay, so back to this example here. In the previous one, we said, okay, like the Brugge-Hatta problem, we said, okay, the solution was like a 115.9, and this is 77.9. And we find out that if we just round to 116 and 78, it's infeasible. Okay, and in this case, we said, well, even though this one is really close to 2, let's just be safe. Round it to 1. Okay. Just want both of them to run. So originally this value is kind of like 1.8 and 1.24. We know that if we run this to 2, we probably have an infeasible solution. Okay, because we won't have enough resource. Let's just be safe. Run it to 1. So run both to 1. Will that be feasible now? You see 1 is here. It's still outside of the feasible region. So you run it either way, you may fall into an infeasible solution. Okay. So that's one. That's the first situation. The second one, if you do get it to be feasible, they may not be optimal. Okay, by running. The example is here. So this is the relaxation. This is the relaxation solution. It's here. So you can see it's x1 is already 2. Okay, and x2 is 1 point something, say 1.8. Okay, and if you round it, we know that we can't round this to 2 because it becomes infeasible. We say, okay, what about we round it to 2 and 1? It is feasible. It's this point here. Okay, so this point is it's 2 and 1. Okay, but is it optimal? There's another point this one here. This point here. It's also a feasible solution, which means it's within the feasible region and both x1, x2 are integers. So in this one, it's a 1, 2 point. And this one is a maximization problem, okay? Comparing this solution to this one. The second one, which is not a result of rounding, gives a better optimal objective function value. Okay, so this illustrates why we don't round them. Okay, so then how do we solve them? We solve them using a method called the branch and the bound. Okay, and first I'll introduce what is a bound. The optimal solution to an LP relaxation of an ILP gives us a bound on the optimal objective function value. Okay, so what does it mean is that for maximization problem, the optimal objective function value you get from the LP relaxation will be always higher. It's like always greater than or equal to the ILP solution's objective function value. Okay, and it's provides, so for maximization problem, the optimal relaxed objective function value is the upper bound on the optimal integer value. Is this understandable? Just by reading it. So for maximization problem, if you take that integer constraint out and solve the problem, the objective function value you get will be always higher, equal to or higher than the true objective function value with the integer constraints. And for minimization problems, the optimal relaxed objective function is the lower bound. So in another word, the ILP's solution, the LP relaxation's objective function value will always be better, if not the same, as the ILP's solution's objective function value. Okay, and this is probably should be understandable here if we just use those examples here. So you see in this case, this is the optimal solution to the LP relaxation. Okay, the objective function value is here, and we can imagine that if it's a ILP, it will be like this, those different integer points within the feasible region. If the integer points happen to fall on this optimal solution, then they will be the same. Otherwise, it will be just within. So you have to always move this level curve inside the feasible region to hit on the integer solution. So you can imagine that the objective function value will be decreased. Okay, so that's why we call that the LP relaxation's objective function value. It gives us the bound, gives us the upper or lower limit. It's always better than the ILP's objective function value. Okay, so with this, then we know, okay, we can simplify. So one way to solve the problem would be we enumerate all those integer points. Okay, we know that, okay, here are those points. What about we just enumerate them, and then we solve for the objective function value. That's one of the methods. Okay, which can be done in this case because we only have what, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 integer solutions that we can calculate. But when the problem gets really big, like in your case study, those values are in thousands, and you can imagine how many combinations that you need to solve. And when we try to find the methods to make the solving faster, you find, okay, because of this bound provided, we can actually just eliminate some of the problems. We solve the ones that make sense. And how do we do that? So here's the branch and the bound method is that you write the problem in the LP relaxation first. Okay. Here, so you write this relaxation. you find this is the optimal solution. That's the objective function value. Okay, and from the graphical solution, we know that where do the optimal solution occur? Graphical solution. Think graphically, where do the optimal solution always occur?
Where they cross.
What's that?
Where they cross.
Where they cross, and what do we call them? What do we call those? Like this point, this point, this point. What do we call them? A corner point. Okay, a corner point. Okay. So remember this one, corner point. So we know that optimal solutions to LP problems always occur on the corner point. Okay. So now we have this one. Then let's see. Okay, we know that we want integer solutions, which means this part and this part. So that's anything here. They are between 2 and 3 for x1. We want to use them. We want to use them because we want integer solutions, right? So any point that's here, we won't use them. So, and these are our feasible integer solutions. So we branch the problem. In a way, we cut that apart. Okay. Well, I'll go back again. Okay. So what we do is that we know we start, for example, so in branch and bound, you choose one decision variable to branch first. In this case, let's just use x1 first. Okay. We use x1. And we know that this entire section here gives us values for x1, which is between 2 and 3. They are not integers. Our integer solutions happen here. And we also know that the optimal solution always occurs at the corner point. So what we're trying to do is to put those integer points to a corner point. And how do we do that? So first, we have to put them on the edge. Okay. On the edges, and then cut them again, then they may become on the corner point. So what we do is we add some constraints to separate the problem into 2. Okay, so the original problem is like this. Okay, if I ask you, how do we separate this problem like this? How do you do that? If I want to separate the original problem into this format. How do you do that? You can add some constraints. So there are 2 problems from the original problem. So what's this problem? It's the original problem plus a constraint. What is that constraint? Can you think about it? Remember, originally it was Cody?
X1 can't be less than, or can't be between 2 and 3.
Can be, then change it to can be.
Okay.
Change it to can be.
X1 can be between 2 and 3.
No. Can be
So,
from 0 to 2 or.
Yeah, that's what I was trying to say.
okay. Okay. So x1. What about this one? Change it to be. X1 is what? We already have x1 is greater than or equal to 0. Okay. Less than or equal to 2, right? Okay. What about this one? X1 is greater than or equal to 3. Okay. That's how we branch the original ILP problem to this way. So we add a x1 less than or equal to 2 and x1 greater than or equal to 3 to the original problem and branch it to 2 different problems. Okay. When we branch it, it looks like something like this. And the attempt is to make those feasible solutions to be on the edge. And later when we cut it again, it will be on the corner point. Okay. For example, can you imagine? So maybe we just cut it here. Then this becomes a corner point. Okay. But before that, once we change the problem, we branch it on x1 and change it to 2 different problems. We solve for both of them because now without the computer you can do it now. Though I won't ask you to do that. Okay, without problem you can do these 2 problems with simplex, right? or a graphical solution. If you have more than 2 decision variables, you can use simplex. Okay. Now you solve both problem. You both solve both problem, and or you solve the simplex you solve the LP relaxation. Okay, without integer constraint. So you solve the LP relax. You get these 2 solutions. So problem 1, you get x1 equal to 2, x2 equals to 2.083. You get the objective function. And the problem 3, you get this one. And because of the bound we said, the ILP solution is always less optimal than its LP relaxation. So comparing these 2 problems, we can continue to branch them. Okay, so which one should we branch? We can do both, but if I ask to choose one to branch, which one should you go first?
Problem 1.
Why?
It's larger.
The objective function is better. Okay, which means it's a solved problem. If we get a solved problem of it, if it's more than, so say if we continue to branch it, and the new objective function is like a little less than that. Let's say it's like the 10.9. Then that means we don't need to continue branch on this one, because the relaxation's objective function value is 9.75. It won't be, even if we continue branch on this one, the objective function value of the true ILP won't be better than 9.75. Which already got like 9.9 here, so we'll continue on this way. Okay, so but in some cases you won't find so once you continue to branch on this problem 1, your new objective function value may be lower than this one, then you will continue to branch on this third problem. Okay, so how do we branch this problem here? What do you think? Now our x2 already integers. If we look at x, if we look at problem 1, if I want to, it's not the integer solution yet, because x2 is still not integer. How can we keep branching it? Like this. So what do? You cut this part, right? So you cut this part. Okay. By adding what kind of constraint?
x2 is less than or equal to 2.
x2 less than or equal to 2. Okay. So less than or equal to 2. So this x2 value is 2.083. Okay. And we can also do x2 greater than or equal to 3. So that's the 2 integers closest to this value. But we know that this part is like infeasible. So we won't want to do that. Okay. So we will add another problem by adding x2 is less than or equal to 2 to continue to branch this problem. Okay. And if we continue to branch this number 3, then we will cut like this. We'll cut this part. Okay, so we continue to branch. We'll get the 2 problems. Problem number 3. So these ones are the original model. Okay, it's like the problem 1. So these one, including the x1 too. So these ones are the original problem 1. And we continue to branch on it. We add x2 less than or equal to 2, x2 greater than or equal to 3. Because it's not very obvious that if x2 is greater than or equal to 3 will be infeasible. In this case, we do have the graphical representation. We know that when x2 is greater than 3, then it's infeasible. But in many cases, we won't be able to know, especially if we don't draw it. So like in the homeworks, you don't need to draw the graphical solution. You just see, okay, how do I branch it? Okay, so you branch it based on the value. Here, x2 is a value between, a non-integer value between 2 and 3. So you branch on 2 and 3. Make one less than or equal to 2, one greater than or equal to 3. That's how you branch these two. Okay, so then you solve these two problems, and you get okay, objective function value. Now we get integer solution, and at the same time, objective function is 10, which is greater than 9.75. So what does that mean?
It's a better.
Is better? That means we are done. Okay, so we don't need to continue to branch on this problem. If this problem, if the objective function value is 9, then we may need to continue branch on here to find out what's the objective function here and comparing them. But in this case, based on that bound we talk about, we said the optimal objective function value of an LP relaxation is always better than its ILP. So this is one. This is LP relaxation. It's always better than its ILP. And because this value is already better than here, that means this 10 is better than any better than the objective function value of any integer solution we can find by continue branching on this problem. So we're done. So that's the optimal solution, optimal objective function value for this entire problem. Okay, any question?
Would it be easier if we could just use the objective function to make the line and then use that as a test?
That works only if you have two variables, right?
Right.
Yeah. So this method we talk about is like it applies to many all the problems that have more than two variables.
Okay.
You can just use this method. So if you have 3 variables, then you probably will branch on, you choose one to branch first, then choose the other one, so x1, 2, 3, for example. You choose to branch x1 first. So when you have 2 subproblems, you may get x1 to be integer. And then you continue to choose one problem to branch to get the second variable to be integer. Then you continue to branch to get the third, fourth variables to be integers. Okay. Any other questions on this? So the summary is like this. The original problem. So I'll ask you to do, I'll ask you to branch this exactly the same problem different way. Okay. So in this specific example, we start from the original problem. We solve its ILP relaxation. LP relaxation. This is the LP relaxation. We solve for it. We find the solutions are not integer. And we chose x1 to branch. Okay, we choose x1 to branch. Because x1 value is a value between 2 and 3, the 2 integers. So we choose 2 and 3 to be the bounds, to be the one that we add as a constraint. So we make it less than equal to 2, greater to 3. That gives us 2 subproblems. Okay, when you have 2 subproblems, you add, so you look at the subproblem, you found x1 is already integer. Sometimes, okay, we'll finish this. So in this case, x2 is a non-integer. So you start to branch on x2. And x2 again is a value between 2 and 3. So you start with 2 and 3 to branch it. And you found one of them gets an integer solution with objective function, which is 10. The other problem is infeasible. Okay, and you compare. This 2 is better than this subproblem's objective function value. So we know we are done here. Note, in some cases, once you branch x2, okay, once you branch x2, x1 may invert back to be a non-integer. If that happens, you continue to branch on x1 in the next step. Okay, so whichever is not an integer, you branch on that one until you find the integer solution. Any questions here? No? Okay. Then I'll ask you guys to do this problem using branch x2 first. Okay, and you have your computer, so you can put the model very quickly to solve them. For example, There's a one homework problem on branch and bound, so once you can do this, then you. So what I did, I just plug the problem quickly into that. Don't use integer, okay? So then I solve the sub problem, get the solution, and solve the different sub problem using computer. So now, is it clear what you need to do? Here I branched on x1. What you need to do now is branch on x2. And create a summary like this. So yours would start like,
So ours will be x2 equals,
you will start from the original. So original. You branch on x2 by adding constraints to x2. Okay. For example, the x2 is 1.8. So which two values should you use to branch it?
1 and 2.
1.8 is between 1 and 2, right? So you use 1 and 2 to branch it. So x2, that's equal to 1, x2 equal 2. These are the two constraints you add. Okay, so ask you to continue. I'll come help. Anyone not clear, let me know. Oh, and I probably should give you the original model. Okay, so here's the original model. You can put it in your. So maximize 2x1 plus 3x2 subject to x1 plus 3x2. That's equal to 8.25. 2.5x1 plus x2 less than equal to 8.75. Okay. x2 greater than equal to 0, and they are integers. Okay, so that's the original problem, okay? And I'll put this one here to show you the steps. To remind you the steps. That's the original model. And you don't need to implement the original model. X1, X2 object function value already given to you. So you can start from subproblem 1 and 2. But you use x2 to branch it. And create a summary of it.
Get my brain working.
Yes.
Where does the, like on this, where does our x2 value come from? Because here 2 and 3,
What's that?
like where you putting this from? Okay, you're saying that there's a one versus this x1. Where is this other, where does x1 value?
X1 value comes from when you solve it.
So you actually,
So in your subproblem 1, you just add one constraint, which is x2 less than equal to 1. Okay, so you will have like that. So you will have several different tabs. Each tab will be a subproblem. Okay, you have many different tabs. So on your tab 1, I would suggest you create subproblem 1 first, and then copy the sheet. Like what we said, copy it here so it will solve. But then change the constraint. Yeah. Now you don't paste, you just copy.
On one sheet.
Right. Okay. Because like if you just copy here, it won't copy it. What I'm saying is that
She wants us to create.
You know this.
No, I didn't have I haven't used Excel. That's I don't know. She said different tasks for each problem.
You can use solver, yeah, but only use the solver
Five
for,
tabs.
just solve the LP relaxation. Solve the sub problems.
I'm not relaxed.
For that,
I don't feel relaxed.
solve the relax one. I think I'll help you relax. You know what to do?
No.
You don't know, okay.
No
So,
idea.
we branch the problem.
Yeah, I understood when you
Yeah.
were explaining.
Can you put the original model in first? To solve the original problem.
So like that x1 equals the 2.769.
Right. Like put this in solver, so
That's
yeah. So you highlight the division, you just create the two cells for division where we create the coefficients.
I see.
And you identify what the problem 1 and 2 will be.
Oh.
So like I'll show you mine. So basically I just put this is my original problem. So this is like the quick way to solve it without any labeling. You don't need to label it. Okay, so that's the original problem. So I highlight those as the decision variables. So these are the two units here, and the resources. I mean the constraints units. I calculate the left hand side here. Those are the right hand side. I implement and solve this. Once I solve this one, I get the original solution. You don't have to solve this one because the solution is already given. It's this one. But then from here, you can create a copy. Create a copy. And make it like a sub problem 1. For sub problem 1, you add a constraint. Because now we are branching on x2. So in this class example, I solve original problem, 2 sub-problem here, another 2. So I have 4, 1, 2, 3, 4, 5, 5. Actually, not this one. Yeah, 5. Infeasible, you solve it too, and the solver will give you, say it's infeasible. So I solve 5 sub-problems. What you are doing now will be similar.
So now, instead of trying to do max, instead of solving for both, we're telling it that it's 2 and it's solving for 1.
No, you don't tell it. We add a constraint x to it.
Oh,
That's it.
okay.
Okay. So you add a constraint to the original model to make it a solved problem.
Oh, whoops.